So let's read it and talk through it. It says, a car starts from rest and accelerates for 6.0 seconds at a rate of 4.0 meters per second squared. It then travels at a constant velocity for 2.0 seconds, and then it decelerates at a rate of 3.0 meters per second squared until it stops. What total distance did the car travel? So I like this better than other problems because there is no part A, B, and C. It's just one question, right? But what we're going to find out is that in order to solve that question, we have to actually do a bunch of little things. So we have motion broken up into kind of regions. At first, it's accelerating 4 meters per second squared. Then it's coasting, no acceleration at all. Then it's decelerating at a different rate, which is it's decelerating at 3 meters per second squared, which is a negative acceleration, right? And then it stops. So we're getting to a final end game where the final velocity is 0. And it also starts from 0 as well because it starts at 0. It says it starts from rest, okay? So when you first look at a problem like this, you try to solve it in one step. But you can't because there's multiple different segments of the motion. And that's really what makes it, I don't want to say tricky, but it just makes it more work. Because there's 3 distinct areas. These equations are only valid when the acceleration is constant. But you can see in this problem the acceleration is changing. The first region, the acceleration, is 4 meters per second squared. Then the acceleration is 0 because we're coasting. And then it says that the deceleration is 3 or negative 3 is what it's going to be. So we have 3 distinct regions, and we have to handle those 3 regions separately. So we're going to essentially calculate the distance traveled in all 3 of those regions and effectively add them up. But it'll be a little simpler than that even. So let's first, instead of trying to write everything down, let's only write down what's appropriate in region number 1. Let's figure out what happens at region number 1. And then we'll consider region 2 and region 3, and we'll string it all together. So we have some initial starting point, on an x-axis right here, let's say. And it says it starts from rest. And we're going to choose our starting point to be an initial position of 0. You can do that, of course. You can just have any 0 point that you want. I'm going to say that this is the 0 point. And the initial velocity is also known, which is, if I put a number here, that'd be helpful, 0 meters per second, right? So that's the initial velocity. And then it says that it accelerates in this region for a total of 6 seconds, and at a rate, gives us the rate of 4.0 meters per second squared. So what I can say is that ultimately, I want to know how far did the car go, and what was its final velocity. I don't know that at the end of this first region. Remember, this is only the first of 3 regions. But I was also told that its acceleration, I'll put this down as 4, the acceleration is 4.00 meters per second squared. And you can think of this as, time as being equal to 0. And then over here, time is being equal to 6.00 seconds, right? So over some time interval, the car, or whatever it is we're talking about, what are we talking about here? A car, yeah. It starts from rest, which in a position of 0, and it accelerates at a known rate for a period of elapsed time of 6 seconds. And this is in the first region. Now, what we want to do is find out the total distance the car has traveled over all 3 regions. But forget about the other 2 regions. Let's just figure out how far it travels during region number 1. How would we solve for that? Well, we can go through and look at our equations of motion, right? We know the initial velocity of the car. We know the acceleration of the car. We know the time elapsed is 6 seconds. And we know its initial position. So we can immediately just run it right through this equation and calculate its final position, the distance traveled in the segment number 1. And since that's what we want to do, that's what we're going to recommend. That's what we're going to do. So we're going to say it's x minus x naught is equal to v naught t plus 1/2 times a times t squared. We're solving for the final position, so we can just run that to the other side. And we can say, x naught plus v naught t plus 1/2 times a times t squared. Now let's put everything in here and see what we get. So what we have is an initial position of 0, right? And the initial velocity is also 0. So we put a 0 in there times time, whatever it is. And then we have only the distance or the gained due to the accelerating part of the motion, 1/2 times the acceleration, which is 4. And we also know the time is 6. So I'll put 6 squared. So really all this boils down to is 1/2 times 4 times 6 squared. And so what you have here is 36 over here, so 6 times 6 is 36, and then this becomes a 2, so 2 times 36. And what you get here is 2 times 36, and so x is equal to 72.0 meters. So what this means is when we start at a known position, then when we end 6 seconds later, the car has moved 72 meters from its starting point. So you're thinking, okay, this is so simple. I'll just do the same thing for the next part of the motion. All right, let's read the next part of the motion. The next part says, it then travels at a constant velocity for 2 seconds. So you're thinking, well, how do I figure out how far it travels in the second part of the motion? But there's a problem, because whenever you calculated the distance, yeah, we figured out the distance over here. We can write it down if we want, but we never calculated how fast it was going at the end of the first region. And that is something we need to know to continue the analysis, because it says in region 2, it then travels at a constant velocity. So you have to know its velocity to calculate anything for region 2. And then you're also going to need to know similar information to do anything with region 3. So even though there is no part A and part B and part C of this problem, there effectively is, because we have region 1, region 2, region 3. We need to inch our way forward. Starting from here, we know where it is now, its final position, which will be the initial position of the next phase, but we need to know its velocity at the end of this region. So how do we figure out the velocity? Well, we can go over here. We know the initial velocity. We know the elapsed time. We know the acceleration. We can easily calculate this. So we'll say that v is equal to v naught plus the acceleration times the time. And so we'll just put this in. The initial velocity is 0, starts from rest. The acceleration was 4, I think it was, yeah, 4. And the time is 6, right? So what do you get? 24, right? So 24, and that's meters per second. So what we basically have figured out is that the final velocity, I'll put it in red over here. The final velocity is 24 meters per second, and the final position was 72 meters away. Now, we did not have this information when we started the problem, but now we do. And we know how far it's gone here. What we're going to do now is consider segment number 2 as its own problem, separate from everything else. And what we're going to say is, what if I just asked you, a car has initial position, initial velocity, and it coasts at a constant velocity, no acceleration at all, for 2 seconds. That's what it says. And then how far does it travel? So we're going to try to figure out how far it goes in region number 2. All right. So let's move over here and draw a similar problem, kind of like a problem number 2. Or part B, I guess you could call it. I guess you could call this part B, even though it's not really a part B. Effectively, it is a part B. And so what we're going to do is say, we have initial conditions here where the initial position of this thing is no longer 0. The initial position is 72 meters away from the origin. And its initial velocity is no longer 0. Its initial velocity is 24.0 meters per second. I just take these numbers directly out of the previous diagram because we say it started here and ended here. This is the starting point for the next segment of the problem, right? And it does this whole thing for, what does it say here? Let me just double check here. For 2 seconds, right? So we can say that this starts, we can say this is t is equal to 0, and elapsed time, t is its own problem, remember? A velocity or a time elapsed of 2 seconds, right? And then what we want to know, as far as like, what is the useful information, we want to know, where does this thing end up? How far away from the origin does it end up? But we know that since it starts out with an initial velocity, and in the second region there is no acceleration, it says constant velocity, we know the final velocity. It's 24 meters per second. The initial and the final velocity don't change in this problem, all right? And we know the acceleration is equal to 0. So I guess all of that stuff comes from that simple sentence where it says, it then travels at a constant velocity for 2 seconds. That's just a few words, but the constant acceleration tells me A is 0. It tells me initial velocity is the same as final velocity, and so now I want to calculate the distance traveled. So what I'm going to do is I'm going to use the same exact equation. We're going to say x minus x naught is equal to v naught t plus 1/2 times a times t squared. I'm going to move the x naught to the other side, so it's going to be the initial position plus v naught t plus 1/2 times a times t squared. All right, now we just stick in everything we know. All All right, so the final position of this thing is going to be equal to the initial position of this thing, which is 72 meters, right? And then plus V naught T, right? V naught is 24, so it's 24. And T, how long does this take? It takes 2 seconds, right? Plus 1/2 AT squared, but A is 0. There is no acceleration here. So A, and then you could say, it doesn't really matter. I would just put 2 here since it's 2 seconds, but it doesn't really matter. This term goes to 0. So really all you're left with is 24 times 2, and then you get that number and you add it to 72. So what you get is 72 plus 48. And so then the final position of this thing works out to 120. We'll just put it as 120 meters, like this. So we go up here and say, all right, the final position we now know is 120 meters. But we have to be careful, or we have to at least interpret what we're talking about. When we say 120 meters, what we're saying is, okay, remember, in part 1 of the problem, we said the origin was here. And when we get an answer of the final position of 72 meters, that is relative to the origin of the coordinate system. Okay, so it's 72 meters away from the x equals 0 position. But then over here, the x naught position was not 0. We said that the car started with an initial position of 72 meters, which means I'm already 72 meters away from the origin. That's where it started. But then when I ended up, this is a coordinate of 120 meters. It's not 120 meters away from here. It's 120 meters as a position coordinate from the origin. So what this 120 really means is that at the end of region 2, remember there's region 1, region 2, region 3, at the end of region 2, I'm actually 120 meters away from the origin, because the x position is the x value is the coordinate value from 0, right? Because that was the origin there. Delta x, if you wanted delta x here, you would subtract these. That would be the distance traveled in region 2 only. But since we started here and we calculated a number here, this is the distance away from the origin. It's a coordinate, just like any x coordinate from the origin. So now we consider region 3. And we know the initial position for region 3, where it's going to be, and we know the initial velocity also, because notice it didn't change in region 2 at all. So we actually have this information, and we can now do what we need to do to write down the information for region 3. So I'll put part C here if you want. You don't really have to. And then we can write these things down. What is the initial position once we start region 3? It's 120 meters away from the origin. That was the final position from before. The initial velocity is given as 24.0 meters per second. Same exact reason. It's because we ended up at the end of the other region there. And what am I trying to find? I want to know where is the coordinate value of the final position of this thing after it moves in this region. And the problem actually states that the car comes to rest. That tells you that it gets to a 0 velocity. So this is the initial velocity. We know the final velocity is equal to 0 meters per second. And then the problem also tells us, if I can get back there, the problem also tells us it decelerates at 3 meters per second squared. So that means that the acceleration is negative 3 meters per second squared. I'm moving this way, and my acceleration is negative, which means I'm starting to slow down. Eventually, I just stop right there. And what position does that actually happen? So we need to figure out what equation to use here. Now, in this part of the problem, it actually doesn't tell me how long it takes. See, the first part, it says it accelerates for 6 seconds. The second part of the problem, it says it is a constant velocity for 2 seconds. But in the third part of the problem, it doesn't tell me how long it takes. It just says it decelerates at a rate of 3 meters per second squared until I reach a stopping point. I don't know the time, in other words. So I could probably find the time, but what other equation could I use here? Well, I look around and I say, what other equations do I have all the information for? I can't really use this because I don't know the time. I can't really use this because I don't know the time. But this one I can use because I know the initial velocity in that region. I know the final velocity in that region. I know the acceleration in that region. I know the initial position in that region. I want to know how far it traveled. And there's no time in this equation, so I'm going to write this one down. I'm going to use that one. So it's going to be v squared is equal to v naught squared plus 2 times a times x minus x naught. That's what I'm going to solve for. And ultimately, what I want to do is I want to solve for x. That's the thing here. Now you can put the numbers in and just and crank through it. That's fine. But let's just do it step by step here. So we'll subtract the v naught squared and that's equal to 2a x minus x naught. All I did was subtract this from both sides, so it moves over. Now I'm going to divide by the 2a, so I have v squared minus v naught squared. I'm going to divide by 2 times a, and on the right, that's going to go away. X minus x naught is all I have. And so finally, I'm going to solve for x. I'm going to say x is equal to all this junk, v squared minus v naught squared over 2a, and I'm going to add x naught to it. So I'm going to add x naught to both sides, and I'm going to flip it around like this. So now I can put everything in. What is the initial velocity in this region? The initial velocity is 24. I'm sorry, this is not the initial velocity. This is a final velocity. My apologies. This is the final velocity. I almost made a mistake and put the wrong thing in there. 0. 0 goes into this region. So 0 squared minus the initial velocity, which is 24. So I'll put 24 meters per second squared. And then we have 2 times the acceleration, but the acceleration is negative in this region, negative 3 meters per second squared. And then after that, I have to add the initial position. The initial position is 120 meters away from the origin. And then I'm going to get the final position, again, in reference to the origin. So when I take 24 squared and then slap a negative sign on front of that, let me go maybe over here. What I'm going to get, when I take 24 squared, put a negative sign on front, I get negative 576. On the denominator, you have negative 6 right here. And then we still have to add 120. Right? And so whenever I take negative 576 divided by negative 6, I get 96. And I'm going to add 120. And then finally, when I add these guys together, 96 and 120, I get 216 meters. Right? So what I figured out is at the end of region 3, I have a coordinate for the x value of this car of 216 meters, and that is in reference to the origin. The x coordinate it's always referenced as a coordinate relative to the origin of your coordinate system. And the origin of our coordinate system is 0, and that's where we started our problem where x naught was 0. And so the answer that we get there is basically the total distance traveled here, the coordinate was 72. And then the total distance traveled in the second one, starting at 72, ended up at 120. This is 120 meters away from the origin. And in region number 3, we started at 120 meters away at the origin, and we ended up at a coordinate of 216. So now we can replace this as 216. So the question says, what is the total distance traveled? The answer is 216 meters total distance. It's just a coordinate at the end of region 3. That is how far it traveled relative to the first region. So when you first start the problem, you might think, I'm going to get the distance, get the distance, get the distance, and add them all together. You actually can do it that way, okay? There's nothing wrong with that. You can find delta x, the distance traveled in region 1. You can rewrite region 2. You know, I'll just go through it real quick. I don't want to do the problem again. But in region 2, instead of starting at 72 and finding a value of 120, you could reset the problem and say, okay, I start at 0 again. And do all the same stuff. How far did I travel? And I would basically get a delta x for region 2. And then whenever I do the third part of the problem, instead of saying I start here, I could say, okay, I start at 0 again. I do the problem, and I'm going to get a value of x relative to the 0 point, which is here. This will basically be a delta x. And then I would take the delta x distance traveled from region 1 and add it to region 2 and add it to region 3. That is exactly the same situation here. Here, all I've elected to do was say that the car starts moving at some initial position here, and in the end of region 1, it ends its motion here. And then in region 2, I say that it starts at the finish point there, and then its new coordinate is here. But again, this is relative to the 0 point, which is at the beginning of region 1. And then I say the region 3 starts at this initial location, and it ends a final coordinate here, but this would then be in relative to the 0 point of the system. Everything in life, you have to have a reference point for everything. Sea level. Airplanes are traveling above sea level. Submarines are below sea level. You know, when you're altitude in an airplane, temperature is relative to 0, whatever the 0 point is. If the 0 is the freezing point of water, it's relative to that. Absolute 0 might be relative for the Kelvin scale. That's the 0 point there. In this problem, the 0 point, we took it to be the start of motion in region 1 of the car, and we never changed it. And so then the coordinate we get at the end is in reference to that, so that's the total distance, but it is not the only way to solve this problem. There are lots of other ways to solve the problem. In fact, I'll tell you one more thing. In this last little bit here, we use this equation to find that distance. And the rationale we did is because I said, well, I want to know that distance, I want to know that coordinate, but I don't know the time in region 3, right? Because I was not given the time, but I could find the time. Look here, if you go up to this equation, I know the initial velocity, I know the final velocity, I'm going to rest. I know the acceleration, it's -3 meters per second squared. I can find the time that it takes to go from here to rest. I can calculate that time. Once I have the time, I can run it through this equation to find the position, and I'll get exactly the same thing as I got here, because this equation comes from substituting in and basically deriving it like that. So there's always more than one way to solve a problem. I tried to do enough to give you a really good flavor for how to solve these problems. The truth is, it does not happen overnight that you know how to do these things. You have to solve them. So what I want you to do is solve this problem, solve all of these problems. And when you feel like you have an intuitive sense of how to use the equations, notice a picture is critical to all of them. Because when you put all the variables down, it's very easy, or it's much easier to identify what equation to use and what I need to do. If you just look at the problem, it's basically impossible. I can't do it. I got to write stuff down. And maybe you're better at it than me, but I can't do it without writing a picture. So please draw the pictures, write the variables, and determine where to go. Solve these, and then follow me on to the next lesson. We're going to talk about free fall motion. And what we're going to learn is that all of these equations that we've learned are applicable to free fall motion, but the only real difference is that we have to change the acceleration here to be the acceleration of gravity. And once we can do that, then we can determine how things fall. And so we're going to do that in the next lesson. So solve these, follow me on to the next lesson where we talk about the equations of motion for free fall motion problems. Learn anything at mathandscience.com.